really excited to have these two here today. So Shalaunda Reeves is an assistant professor in the Department of Theory and Practice in Teacher Education. Dr. Reeves' research focuses on how people learn STEM topics in different contexts, including extended reality, classrooms, laboratories, and organizations. Her human health-specific expertise includes designing training experiences utilizing extended reality to improve the knowledge and skills of nursing and pharmacy students and current practitioners in the health professional schools. And her collaborator is Jared Porter, a professor and associate department head in the Department of Kinesiology, Recreation, and Sport Studies. Dr. Porter's research investigates how humans learn motor skills and how the human nervous system generates skillful movements. His research has practical applications to various settings such as military mission planning and performance, patient rehabilitation, clinical and occupational training venues. And with that, I am going to turn it over to Dr. Reeves and Dr. Porter. Thank you so much for being here.
Thank you for having us. So I'm going to attempt to share my screen. See how this works. I think we're good. Can everyone see it? All
yes.
right. So I'm Shalaunda Reeves. And again, my collaborator is Dr. Jared Porter. Oops, there we go. And so just to kind of give you a brief synopsis about my research, there's two big questions that kind of overarch my research agenda. And that's how can learning experience be designed, implemented, and then properly measured to benefit domain-specific education? And then the second one is, in what ways can disciplinary literacy perspectives? So disciplinary literacy is a theory that's typical for how people learn to read, but then literacy as a whole. And I'm interested in that perspective because domains are cultures, and disciplinary literacy looks at domains as cultures and how do we enculturate individuals into various domains. And so from this perspective, I look at ways I can support access and opportunities to learn within various health and health-related domains. So to give you just kind of a brief view of the work that I've done in VR more specifically, I developed a virtual Ford nuclear reactor. So the Ford nuclear reactor in Michigan was decommissioned in 2003. And so a university needed help supporting students doing iron rod experiments. And of course, as you know, you can't actually touch the iron rods. And so how do we support them doing that? How we measure performance in this was that students had to be able to measure their data analysis to determine a quantity of interest. And then we also designed this to familiarize with the components and operations of a nuclear reactor, something that they wouldn't have had otherwise. Another training I created was for a building construction course for augmented tectonics. Students typically engage with the material on paper. They really didn't understand how the three-dimension materials that they were learning about performed within space. And so we were really hoping to help students be able to interpret, synthesize, and make two-dimensional representations for the production of three-dimensional construction, and then help them understand scale. That's really a big problem that most students have. And then the physical constraints of certain materials in relation to their visual spatial reasoning and understanding. And then the last one was for nursing. I worked with nursing subject matter experts to develop what we called under the skin. So it was for oncology nurses and pharmacy techs who had patients with ports. And so if the port leaked, it was very hard for them to recognize when certain signs and symptoms, because it doesn't happen often it also happens under the skin, and before they recognize it, it has dramatic effect on the body. And so here you see it's showing them kind of the spread of the leak, and then therefore the deterioration of cells in that if they do not follow proper protocols. And then we really wanted to help them recognize that skin tone matter. A leak would look different on a person of my skin tone versus somebody with Dr. Porter's skin tone. And then discerning situations, if a leak happened intravenous versus outside of it. And so that's really where my research has led me into the nursing realm. Dr. Porter?
Thank you so much. So my research is really driven to try to answer kind of three basic questions and understanding a variety of topics related to those three questions. So as you heard a little bit in the introduction, I'm fundamentally interested in trying to understand how humans learn motor skills. How do we learn how to move? And then to take that a step further, I'm really inquisitive on the ideas of understanding how does our nervous system take those learned behaviors and then generate movement, right? Our brain has to tell our body what to do. And then another central theme in a lot of my work has been trying to understand how humans learn skills, how the nervous system generates movement, but within human machine interactions. So many times when you're performing motor skills like driving your car, you're on your smartphone responding to a text message, maybe you're working on a paper using a computer, you're climbing a ladder to fix something on your roof, and you're using a variety of power tools to do that. Many times when we're executing skills out in the real world, we are interacting with machines. And so through the process of thinking about motor skill performance and learning, a central part of that then becomes, well, how do we then interact with the machines to do those types of things effectively? So Dr. Reeves, you could take it to the next slide, please. So I always like to think about human behavior in terms of this interactive triangle that you see here, is that, you know, the human is receiving lots of information, and that information can come in through the eyes, through the ears, through proprioceptors throughout the body. And then all of that information has to get processed. And then if the human processes that information correctly, it should generate a efficient performance, which then creates this feedback loop. Then the person gets more information, and then that has to get processed and so on. And as you'll see in the upcoming slides, a lot of my recent work has dealt with military populations. So I get to work with a lot of pilots, for example. And so we're interested in kind of in these interactions of how does the human pilot process information to then operate the aircraft. And many times these military pilots are in dynamic environments. And so they have to be very reactive, but also be proactive because they have to try to predict the future in a lot of ways. So we get into a lot of these questions of these three-way interactions between information, processing, and performance. And then I'll go through the next couple of slides to share some examples of that. So next slide, please. So we've been doing quite a lot of work over the years with training Air Force pilots. And so here you see a picture of a young Air Force pilot learning how to fly a jet for the first time. And so a lot of that initial training is happening through virtual reality, and in some ways even using augmented reality. And so the Air Force has been making quite a lot of investments in developing these types of technologies to train initial pilots through different types of protocols because it's safe. You know, they're on the ground. They don't have to put them up in the air to practice these different chaos scenarios. It's also very cost effective. You know, it costs quite a lot of money to fly a jet in particular. And so just to do a basic training mission can easily get into tens of thousands of dollars just in fuel cost. So again, being able to do some of these trainings on the ground in virtual reality provides a really nice return on that type of investment. Next slide, please. So here's a photograph from another study. This is with an Army project working with Army helicopter pilots. And so a lot of the work that we do in the motor behavior lab on campus deals with issues related to cognitive workload. And so a lot of times pilots are asked to do many, many things when they're operating an aircraft, which operating an aircraft is already really complicated by itself. But then if the pilot then has to process a bunch of additional information, it really reduces their decision-making capabilities and also reduces their capability to operate the aircraft effectively. And so we've done a variety of studies understanding how cognitive workload within a pilot population changes as they're interacting, one, with the aircraft, but as you see in this picture, this pilot's also wearing a head-mounted display or an HMD. And that HMD is an augmented reality lens. So there's a whole bunch of information that gets projected in the field of view for that pilot. So they not only have to monitor the cockpit dash, but also what's happening in front of them. And so we were very curious to understand, well, how does all that information that's coming into the pilot's brain get processed and then ultimately affect performance? And this study was revealing because the whole assumption was that this head-mounted display would help the pilots, that it would improve their cognitive processing capability, which would then translate into better aircraft operations. Our research showed the exact opposite, that adding this head-mounted display actually saturated the pilot's cognitive capabilities and then resulted in them having reduced operation capability. So one of the things we might talk about a little bit later is I'm an inherent skeptic with all of this stuff. So my assumption becomes that the technology doesn't work, and we should be collecting data to validate it, to design it better, and then get into topics related to transfer of learning. And so this is just one quick example of how testing this type of technology within a human performance operation is really, really important. So we don't just assume that it's helpful, we need to validate it. Next slide, please. And then similarly, we've done work with military operations with marksmanship training and assessments. And so we have in the motor behavior lab a similar, like to the picture you see here, a marksmanship simulation system that's totally interactive. So military personnel or law enforcement can come in a very safe environment, shoot these guns, which are just powered by gas. They don't fire any bullets, but they can interact with this screen. So we can create a variety of virtual reality situations that are projected and do, again, mission planning, marksmanship assessments, in really high risk environments that are simulated, and then transfer that out to the field to see, does the marksmanship qualification standard improve? Does it not improve? How can we help these operators prepare for upcoming missions that they might be encountering, which are typically very high risk environments? Next slide, please. Ezra, I'm going to turn it back over to Dr. Reeves a little bit to talk about some of our combined efforts and collaborations.
So again, as you see, Dr. Porter and I have similar but very distinct kind of research agendas. Mine is more, how can learning experience be designed and implemented and properly measured, as you heard him speak about, to benefit domain-specific education, plus his of, can motor skill performance be optimized through MR technology, mixed reality, and then does mixed reality technology facilitate transfer of learning? To our combined effort of really trying to understand for whom and under what conditions can mixed reality be designed and implemented to support greater gains in motor learning. So back to what Dr. Porter said, we're making no assumptions here. We're not assuming that it works. We are really trying to see how do we best understand how the design influences whether it works or not, for whom and under what conditions. Is it great for novices? For someone who's already an expert, can we upskill? Can we reskill? And then, of course, measurement, because how you measure something matters, you know, for whether you're being able to determine its effectiveness. And so what we're going to do now is just kind of show you how we've shown you what I do, what Dr. Porter does. We've kind of given you our combined efforts. And so the next few slides is really going to highlight how our work has come together in our research.
So I'll talk next about this very recent study. So this is work that was done by a doctoral student who just graduated that both Dr. Reeves and I worked with. And so what we were interested in trying to investigate in this study was the comparison of practicing and learning a motor skill in virtual reality in comparison to practicing the exact same motor skill in the real world. So in this study, we actually used golf putting as the motor skill because it was pretty easy to find a bunch of novices. And then we could also pretty easily create a virtual simulation with a head mounted virtual reality system that looked exactly like the real world golf putting task. And so you see a bunch of pictures kind of on the left side of the screen here. So in the upper left is just a picture of the virtual reality headset and hand controllers that we used in this study. And then, so what we did is the participants that were in the virtual reality group came in, put on a headset, and when they put on the headset, they saw the exact same golf putting surface that you see in the bottom picture, which coincidentally was the putting surface that the other half of the participants practiced on. So those participants came in and actually hit golf balls, got to stand on the putting surface, went through all the motions, felt the weight of the club, felt the contact with the club to the ball. But the virtual reality group put on their headset and then just got to see the same image. And then when they looked down at their hands, they would see a virtual golf club extending out. And they would look down at the floor and they would see a virtual golf ball. In reality, there was no golf club in their hand. There was no golf ball in the environment, but they could virtually interact with the golf club and the golf ball and practice putting. And then you see in the kind of the upper right picture as an example of the EEG headset that we use. So this measures brain activity in the four basic regions that you see in the bottom right picture: the parietal lobe, frontal lobe, temporal lobe, and the occipital lobe of the human brain. And so again, the participants would come in, half of them would practice putting golf balls in virtual reality, and we measure their brain activity, and they practiced over several days. The other half of the participants would come in and actually physically hit golf balls over several days, and we measure their brain activity. And this study, found some pretty noteworthy findings. Most importantly, I think, is that after several days of practice, we found that there were no significant differences in either group of participants when it actually came to hitting golf balls. So what that tells us is that when the participants practice hitting golf balls in virtual reality, they learn that skill just as effectively as the participants that actually physically hit the golf balls. And then we gave them transfer of learning assessments like a couple of days later following practice, and still no differences. So that tells us that learning how to hit these golf balls in virtual reality transferred to the real world. So they were able to take off the headset. We actually gave them a golf club, asked them to hit golf balls, and they were significantly better than when they started. And they were no different than the group that had been hitting golf balls in real life for the previous several days. And then we looked at brain function and found no difference, right? Those data tell us that when you hit golf balls in virtual reality, your brain is operating no differently than it does when you hit golf balls in real life. And then what we also see here is when it came to looking at how perceptual information was perceived by the brain, there doesn't appear to be any difference. So virtual reality was able to deliver all the sufficient sensory information that was needed to effectively learn the motor skill. And so we're doing a bunch of work currently and then in the near future that's going to try to extend these types of findings. So this becomes a really nice combination of both the work that Dr. Reeves has been working on and the stuff that I've been working on in the past.
And so again, now we're moving it from a very decontextualized understanding, hitting the golf balls, to a more contextualized experience within the health field. So we worked with graduate nursing students to teach central line exclusively for their competency exam. So we had two sets of students. One student went through training of central line in the traditional format, and then another set used AR exclusively. The two differences that we really wanted to look at was their time on task. Students in the AR, because it did not require a faculty presence, they were able to go to the AR lab as many times as possible, as they chose to continue to practice this skill in order to prepare for their competency exam. And so our findings show that AR learning was effective, very similar to what Dr. Porter said in the previous slide. All students did pass the practical exam, engaging. They found the experience engaging, motivating, and enjoyable. And then another thing we noticed was that practice time was the only significant determinant of predicted test scores. And so again, we're focusing on number of times that students are engaging with an experience in relation to their success. And so that leads us to our future research, where we're hoping to understand a little more about XR in relation to graduate nursing or nursing education as a whole. Dr. Porter?
Yeah, so can you guys hear me? Is it okay? Yeah, okay, awesome. Yeah, the mute thing was flashing on my screen, so awesome. Okay, good. I was a little worried. So where we see our work going is, we are really motivated to understand how, just furthering our understanding of how we can use these types of XR technologies to really effectively measure learning and retention of applied motor skills, and really comparing that to traditional instruction. These are emerging technologies that are starting to become more widely used, but they're not really being validated. So we're wanting to put it in the proper context into an educational environment and understand how these types of, again, technologies can be used to teach and help people learn motor skills effectively. And then we want to try to extend this also into using artificial intelligence, and then trying to make this technology adaptable in a way that can really begin to individualize the learning environment. And so that way the learner can interact with these technologies, and the technologies are adapting to the needs of those types of learners based upon that particular context that they're in. And then taking it even a step further, trying to find out if any of these things are task dependent, and maybe there are certain types of tasks or certain types of environments or some particular types of context that lend themselves to be more effective when it comes to using these types of technologies to improve human learning, human performance, the human experience, and then, accelerate training programs, thinking about workforce education topics, and creating, safer learning environments, things like that. And then lastly, I think we are really interested in the design questions, right? How can we take these types of data and then build better technologies to really try to optimize human performance? So I think in the future, that's where we really see our work merging together even deeper, is to try to build better technologies across a variety of human experiences and occupational settings and learning environments. And again, making sure that this technology works, and that it's making the human a better performer in the world that they live in. Oh, you're on mute, Dr. Reeves.
Are there any questions?
Thank you guys for that awesome talk. So I really want to encourage people, this is your time to ask questions now. I am going to start by saying, I think I'm going to get a virtual reality golf set and see if it helps my game.
Where do you sign up to participate in the golf set?
Yes.
We have plenty of consent forms available. Yeah, I can give you the information for the lab, and we'd love to have you come by. Yeah,
well, I'm
sure.
definitely a novice, so I think I would qualify.
You're not alone. Yeah.
I just wanted to say that everyone should be able to unmute yourselves if you want to ask a question in person, or you may put them in the chat if you're not able to do that.
I have a question, and it's totally related. I mean, I think everybody got a little stuck on the golf thing. My father is an avid golfer and just recently got a golf simulator. And so you actually hit the balls into the screen. And I was wondering if there had been any studies about using a virtual reality, because you mentioned there was no golf ball and golf club versus using like a simulator that adds like the actual physical motor component? Because I would think that like for a skill like golf, well, not a astounding amount of strength that's required, there is some strength that is required and like in the friction and that kind of thing. And so I was just wondering if you guys had thought about that aspect and what that adds or takes away from the process.
Yeah, there's a lot to unpack in that question. It's a good one. So, I mean, I think let me go back a step, and because I want to note that, like in the study that we did, participants only putted golf balls, so they weren't driving. So yeah, so I think you bring up a really good point, and that is, to drive a golf ball, the further you are from the hole, the more force you have to apply to project that little ball towards the target. Oddly enough, in our literature review that we've done in both virtual reality at large and then virtual reality within golf training in particular, there hasn't been any studies that I've been able to find that shows that the type of golf simulation task that you described actually transfers to the golf course. And so I think what studies generally show is that if you are, hitting a golf ball like into a screen and it's calculating where that ball goes, you can practice in that environment and get better at that. I'm going to call it a game, right? You can get better at that game, but the data generally show that when you go out to the actual golf course and you line up on a tee and hit the ball, it doesn't transfer, right? Because in motor learning, there's this principle that we call practice specificity. And that just means that learning in general is very specific to the environment that you practice in. And unfortunately, there's very little transfer out of that environment. So if you play that golfing game, you get better at the game, but you may not get better at actually playing golf. And so I think what our study begins to demonstrate is that through virtual reality training, where you have a head-mounted display, right? You put on this headset, and now you're immersed in the environment. You get a full understanding of dimension. You get an understanding of force production. And again, our study only had folks practice for a few days, but we saw though that when they took off the headset after, I think it was 3 days of practice in the study that I talked about in this slide deck, after 3 days of practice in virtual reality, when they were given a golf club, they were better. So they were learning actually how to putt a golf ball more accurately. So I think to try to get any sort of benefit from virtual reality, what the studies are generally showing across the board is that you really need to immerse people in that environment. You want to make it as real as you can, or as close as it is to real life. So hitting a golf ball into a flat screen is pretty different than hitting a golf ball through a three-dimensional environment outside. And so, so far, I think the data show that your father may be getting better at that golf game, but he may not be better on the golf course as a result, which can be pretty frustrating.
Yeah, I don't think I'm going to share that information with him.
Yeah.
He's really enjoying it though. Thinking about like the technical aspects, like learning how to control like some different spin that I don't know that much about golf. He's all into it. And so it's helping him think about it differently. And so it's a different aspect of learning that I think he's really trying to do, rather than saying every bit of this game is going to translate into all of a sudden I'm going to be out there, on the tour or anything like that. But that's really interesting. My mind is going a million different directions with my own research, and stroke and rehabilitation. And then also kind of thinking about this with having just tested out my dad's golf simulator a couple days ago. So
yeah,
it was fun.
Yeah, well, I think you make another good point, and that is, I think it's always important in any sort of learning environment to define the kind of the goals and objectives. And so, like for your dad, maybe the goal is just to kind of have fun, maybe get some movement or exercise, and just learn something different. And if that's the goal, then play the game. Awesome, that's a win. But if your dad aspires to join the PGA and become a professional golfer, and that's going to be his livelihood, that may not be the best method, to do that. He probably needs to get out on the golf course and play the game, right? Do the thing. And so it's really important to always define, what do I want to get out of this? What are the goals? What are the objectives? And then build an environment that gets you to those goals and objectives efficiently.
I was kind of curious if you asked any of the nursing students or like got their opinions on like, I guess, the pressure or stress related with the activities, because I can imagine it's a lot more stressful, or you'd have a lot of pressure on yourself to try and place a central line on a human when you're not very confident with it versus doing it virtual reality, and if that affected results.
So these students were graduate students, so most of them had been in clinical settings. And again, that kind of goes back to the for whom part of it. I don't think they felt the pressure because, you know, they were typically used to working with patients. But I do feel like they miss the feedback from the faculty advisor or the faculty instructor who was typically giving them tips and tricks of the trade. And so that's another aspect that you saw in our kind of where we want to go from here is how do you design an experience that support, as Dr. Porter said, the total experience, right? You can't just have one aspect. We did in our initial one because we were trying to keep our research in a box in the sense like this one thing, but you notice, okay, if I design in my iteration, I have to design for some form of feedback because not only is it necessary in their practice, but they miss it. Like that was something that they actually said they wanted. So I don't think that they were super nervous. They did come to the skills lab quite a bit. So they did enjoy that part of it, where in the traditional format, you only had skill lab maybe once or twice a week. But this one, if they were at the lab for another reason, or if they were just on campus, they would always stop by and practice a few rounds of central line and then leave. And so I thought that was pretty interesting.
So I'm a pathologist, veterinary pathologist, and I could see application. I mean, there's the one, the benefit of having that animal, but I could see application of this in, for autopsy and for necropsy both, so humans or animals, and being able to, because in the veterinary world, we have so many different species. And be able to have something like this where you could actually have the virtual learning of where you're opening a bird versus a frog versus a horse versus a cow and going through the organs and such. That would be, I think, something really useful, and probably the same in the, in the human world, to be able to open a human. Have you thought about what's your next step? Like, how are you going to expand it?
What you couldn't see, because it's so hard taking good pictures of the XR, but there is an overlay that he's actually looking at. So, when you do, well, you don't, I don't know if you know, but in central line, there's so much happening in there where you can nick. And so it is an overlay for the students to kind of see the other aspects of the body that they need to pay attention to or visualize, in a sense, as they're doing the central line. Nice. And so one of the things Dr. Porter and I are currently working on is an XR experience for teaching nurses how to do NG tube placement. And then again, providing that kind of visualization of, you're in the throat, now you're in the, okay, be careful, don't go into the lungs, and then providing sensors as well, that when they do go into a lung, it will provide that type of feedback. So for you, the overlay would change based on the type of animal, and then help them recognize like, oh, this animal, I don't know how animals are structured, but I'm assuming some parts are not always where the other animal parts are.
Yeah.
And I'll kind of add too, I've had a similar experience with some of my military work not in a medical situation, but in a mechanical situation. Whereas you have a major problem for the military, especially when they're in a deployed environment or an austere environment, is that, let's say, a particular type of military tank breaks. The mechanic you need, so maybe that tank is operating in, I'm just going to make it this, I'll say Germany. But the mechanic who specializes in that repair is in France. And then the parts that you need are in Arizona. And so you have to then like fly the part from Arizona to Germany, fly the mechanic, because like they're not a specialist in this thing. So we've created a virtual reality training protocol to where maybe you have a mechanic with the tank. They're not a specialist in the thing, but they can put on a VR headset and connect to the specialist who's in another country, and then maybe 3D print a part in the field, so you don't have to fly these things all around the world. And so I think it's a bit of an analogy to like anatomy. And so like these animal species change, and so some of the anatomical structures change, much like the mechanics of a vehicle, or an aircraft, so there's a common thing where an airplane has a problem and has to emergency land, and then now you don't have a mechanic to fix it. And so we've done work with military thinking like, how can we connect these different specialists virtually so they can kind of teach or guide, like, hey, do this, do that, or maybe using an augmented reality where they can look at the machine and get some step-by-step instructions about like, here's what you do. And these new military aircraft in particular are intelligent. They have these artificial intelligent platforms that can communicate very efficiently to guide people through to solve these problems. So I think that there's a future where you can do the same types of things in veterinary medicine, or in human medicine or whatever it might be. And so we're hopeful that our work can get us closer to using these types of technologies to solve real world problems. And so it's fun to think about it in veterinary medicine. Yeah, that's kind of a new one, but it's a problem.
Yeah, that would be really awesome, especially if students could actually be doing it. And Dr. Greenacre reminded me that we have an a table.
Anatomage.
Yes. Oh yeah, you can tell them about it.
Oh, it's amazing. There's this table, and it's basically a 6x3 computer screen that is horizontal, and they have human anatomy there, and every kind of animal anatomy you can think of, birds and horses, everything. And you can, it's based on a 3D scanning of those bodies. And so then you can go to a specific organ, you can enlarge it, you can follow certain organs throughout the whole, or, follow the veins all throughout the body if you want to. You can just, and you can make all the muscles disappear and just look at all the veins. You can look at just all the artery. It's just amazing. So if you get a chance, UTK does have an anatomage table. It's at the UT main library. You have to just sign up for it to spend some time on it. I was having a lot of fun with it, and I'll warn you, the screen after about an hour gave me a headache, because of all I don't know what was coming off of it, but so I would say limit your time on it, but it is amazing.
I've actually, one of my collaborators at University of Michigan, they have one, and they told me about the UTK. Apparently word gets out about what you guys have over there. And I've been really interested in implementing, like understanding how it's implemented within the larger curriculum experience. So I'll have to reach out to you to pick your brain about that.
Yeah, and you make a good point too, like the dosage, and that's a kind of a common thing, that if you spend too much time in these virtual environments, it can cause headaches or nausea or motion sickness. And so I think as the technology gets better, hopefully it'll solve some of those problems. But I think that there have been some recent data that come out and actually show that if the technology is too good, it actually becomes really difficult for our brain to process the virtual component of that. So it seems like in some ways that we we may not want to get too close to reality, because that might cause some serious problems for our nervous system. And so I think if you guys have experienced the new Apple headset that's come out, that's been one of the big pushbacks with that new headset, is actually too good. The optics are too clear. And if you spend too much time in it, people are reporting some very serious neurological problems. And so it's like we may actually need to make it a little bit worse if the user is going to use it for a long period of time. But we'll see. This is all brand new stuff.
So do we know what's going on that's causing that? It's just because you're sensing you're one place when you're actually another place, or what is it that's causing the disconnect?
I don't know. I haven't seen data. It's just reports. People are saying that it's a little too real. And I think we see this, there's a term in robotics, I forget what it is, but the same, like if robots are too human-like, we kind of repel them. They kind of creep us out. And I forget the terminology for that, but I think we might see maybe in virtual reality something similar. Like this is too real, and people just don't like it. They start to get anxiety a little bit. It seems like the actual neurological mechanism, I don't know. I'm not sure. I haven't tested it, but I'd like to, hopefully in the future. So I think we might see the dosage though, and just how real is this reality. And so I don't know. So I don't know that I don't have an answer to the question, but it seems like we might be getting to that point though. The technology is getting so good that it might be too good. And so it goes back to this issue of dosage. I think we see that. And so, for example, like in the Air Force, United States Air Force, if a pilot does a virtual reality simulator, they are required to wait, based on how long they're in the simulator, they are required to wait a certain number of minutes before they can actually get into an aircraft, because there's data that show that the transfer from a virtual reality environment to a real world environment, there is a bit of a delay in the brain's ability in some way to kind of get back to reality. And so if that transition happens too quickly, especially if it's a high fidelity simulator, but I don't know the actual mechanism yet. We're hoping to dig deeper into some of those things. Any other questions out there?
I have a question.
Yeah.
Kind of following up on what you were saying earlier, Dr. Porter, about the mechanic scenario. For like the medical learning aspect of it, what are the implications, I guess, for training medical students or professionals in remote areas, or I don't know, hard to get to places, or even like, in countries that are at war where you can't get training in, that kind of thing. I don't know if that made sense, but.
Well, it does. And I can tell you right now, this is being tested in the Ukraine. And so Ukraine field combat physicians have the ability. I got to be careful I don't say anything that's classified, because I have some non-disclosure agreements in place with the Department of Defense. I think all this stuff I'm about to say is public. I hope it is. But, so a Ukraine military combat physician who is in an austere environment can put on a augmented reality headset and connect with a U.S. combat physician that's in Poland. And so like the U.S. combat physician is not allowed to be in Ukraine, but they can connect. And then that American soldier who's a trained physician can provide instruction and feedback in the field through these AR headsets. And so I think we're getting closer. And if you follow DARPA research or DoD research, they are making huge investments in developing this type of technology for this exact function, to put somebody in an austere environment and they can connect, through AR, VR, some sort of mixed reality, whatever you want to call it, to get real-time instruction, get feedback, and then, provide information to them in a real time. I've not tested any of those things, but I know they're being developed right now. And I think that there's a future that's not too far down the road where this is going to happen in hospitals, in America. Becomes kind of a common thing where we become more connected. But I think we need to do a lot more research to make sure this is actually a good thing, that it works, that this type of connection is valid and isn't causing more harm than good. So I think we'll see, as unfortunately, it looks like the conflict in Ukraine is not going to end anytime soon. So it's going to provide a lot of data, and so we'll see. So I don't know if that answers your question at all, but I think there could be solutions achieved through this development of technology.
So I think it also goes back to what Dr. Porter was saying earlier about the objective of it. So if the objective of the experience is to provide access when there was no access prior, then your measure of success changes, right? It's like they had no access, no idea how to do this thing. We have provided that. To what degree, to what extent, we still don't know, but that would then change kind of how you measure the success of it within spaces that do not have the traditional access, or be it rural population, country, whatever the reason.
Yeah, and another thing that comes up in our work quite a bit is just, especially in nursing, is there's a very real shortage of nursing instructors. And I think that's true for all instructors, certainly in medical fields, but nursing in particular. You look at a class of 40 nursing students and there might be one or two instructors. And so the students have to wait long periods of time to get any sort of feedback or instruction, because the instructors are just hopping around trying to get to the students as quickly as possible. So another thing we're interested in doing is thinking about how can we maybe develop some technology to try to solve some of those problems. So with artificial intelligence and these adaptive systems that we're developing, it'd be great if nursing students or medical school students or whomever it might be can put on a headset in a training environment and get some feedback, get some instruction. And then so they're still interacting with their human instructor, but instead of them just kind of standing there for 20 minutes waiting for some feedback, the adaptive headset can kind of be coaching them a little bit. And then when they interact with their human teacher, they're like, okay, let's validate this. You're doing this right. And so again, I think we're very motivated to try to solve problems with the technology, not just create a new toy. We don't want to do that.
Some of us see them as toys.
Sure. Well, they can be a very fun toy. Yeah.
Fun way to learn.
Yeah. But the learning is the key thing. Yeah. To learn is the goal. Yeah. To change behavior in a positive way.
Anything else? This has been really very interesting and very educational, because learning what's possible and where we are in the process of developing some of these tools is going to be it's game changing. It's going to really be enriching for the medical field and so many other fields as well. So using it in a good way.
I was just going to, echo some of the work that Dr. Reeves talked about that she's done with, training people to work in dangerous environments, like with nuclear reactors. Like it's hard to practice in that environment. You just can't. It's too dangerous. And so simulating these things becomes really important. So I think it's exciting to think about the future where we can help train medical practitioners, but then also firefighters, folks that are working with toxic chemicals, and just you go down the list of things. Like there's potentially some wonderful solutions that can come out of this technology if we do some good science to inform the design of these things. Yeah.
And it's interesting because we actually designed that right after the the meltdown in, was it Japan, I believe, with their nuclear reactor. And the problem, if you guys ever read up on it, the problem that they had was that most students didn't know what to do when the reactor didn't cool. The assumption is the water will come on, it will cool the reactor down. And so because a lot of them, a lot of, like at where we were, the Ford nuclear reactor had been decommissioned since 2003. A lot of the students read and learned about it in theory, but then when it actually happened, the water didn't cool down the reactor. They didn't know what to do. And so then it just became a series of events that, that were catastrophic in the end, but could have possibly been really less damage possibly if learners were able to really understand what to do without certain events.
Well, I think we're about out of time. So thank you both for being here. Really, really appreciate it. And everyone can share with others, because we always get questions, that this will be available on our website under the seminar series. We have links to all of our past seminars. So it's always possible to see them even when you're not able to attend in real time. All right.
Thanks so much for everyone for attending and giving us your time.
Yeah, thanks for the invitation. It's been great.
You bet. And thank you.
Thank you, guys.
See you all.